So in this lesson, we're going to deal with polynomial inequalities. So here's an example. We want to solve this inequality. This is Quartic function. That means power of 4 inequality. All right. Now we're going to use the algebraic method. Then we're going to translate that into a graphic solution so they can see it visually, and then we go from there. Step 1, we're going to treat it just like an equation. This inequality, we're going to treat it like an equation, so equal to 0. And we're going to use the factor theorem to actually find the x-intercepts or the roots or the zeros of this polynomial function. All right. And the factor theorem is basically says that if this polynomial has any integral zeros, so it has to be factors of -5. Okay, that's what we're going to do. All right, let's write up all the factors of -5. So factors of -5, plus or minus 1, plus or minus 5. All right, now we're going to go through and we're going to substitute each of these and find the function f of 1, f of -1, f of 5, and then the last thing is f of -5. Okay, I went ahead and used the factor theorem for each one of these. So I used the factors of -5, 1, -1, 5, and -5, and I used the f of 1 values, and then the f of 1 is that when I plug in the actual possible factor, if the value of f of 1, f of that possible 0 is equal to 0 at the end, when you do the math, then the 1 is x equals to 1 is the x-intercept, one of the x-intercepts, and in this case it is. And I chose just the first one to give an example, but you do the same thing for each one of these. F of -1, you plug in -1 in here for x, and then this next one is 5, you plug in 5 for all the x's here, and then notice that the first three, they give you 0, but the last one, f of -5, it doesn't give you 0. Okay, now that we have these three roots, we are not completely sure that the fourth root exists or it does not, but because this is a quartic function, we know that it has to pass through the x-axis. Maximum number of times will be 4 times, and minimum could be 0. But in this case it's 3. So that means that it could have another one, that either there is a double 0, that means double roots, that means that the graph touches the x-axis and bounces off, or that the next one is not an integer value for the x-intercepts. To do that, we are going to use x minus 1 and x plus 1 factor. We put them together, multiply them together, you get x squared minus 1. This is the difference of the squares, and we're going to use long division. Okay, that's what we're doing right now to find out exactly what is happening to the last two. So we know that after doing this, one of the solutions will end up being 5 for sure, but we want to know what would be the next solution. I'm going to actually talk about the first step, and then after that I will fast forward this. But for a long division, so we're looking at the x to the power of 4 here. So what should we multiply x squared by to get x to the 4th? So that would be x squared. So I'm multiplying x squared one term at a time to get this right there. Just a review of long division. All right, when you do this, notice that you don't have x cubed term. So you need to still include that. You put a 0x cubed in there, and then you multiply x squared by minus 1, you get minus x squared. And then you have to subtract. So this would be 0, and here would be minus 6x cubed, and then here will be plus 5x squared plus 6x. We're going to bring the 6x down, and then we are going to go to the next step. What should we multiply x squared by to get minus x cubed? And in this case will end up being minus 6x x, and then we're going to go through again. So this would be minus 6 x cubed, and in this case we don't have x squared, so it would be plus 0x squared. The next one will be plus 6x, and then now we're going to go through and then do the last step. Okay, 0, this would be 5x squared, this is 0, and then we're going to bring the last constant down, that would be minus 5, and the last step is we're going to add plus 5, and then this will give us 5x, this would give us 5x squared minus 5, and that would give us 0 and 0. And now we know that we have this as our dividend, which is x squared minus 6x plus 5, and if you factor that, that will give us x minus 1, x minus 5, and these are the last two factors. Now if you go back up and see the other values, we already have a minus 1 here. So now there are actually, in this case, 1. We already have 1 in here, so we now have 2 zeros that are equal to each other. So that means we have a double root. That means we have the following 4 roots for this function. We have x equals to 1, and again x equals to 1, so we have those 2. Then we have x equals to negative 1, and then x equals to 5. Those are the 4 roots, and now we're going to implement the graphic solution using these values. Okay, the last step is I just sketch, very rough sketch of the function, the polynomial function that we have originally on top, right? The Quartic, and that's what you will get using this information. We have minus 1, we have 1, a double 0, so the graph touches it, and then drops down, and then it drops down to a certain level, which we don't really care at this point. We are not trying to find the minimum value of this function, so we don't care, but we do know that as once it's down, it comes back up and it will pass through 5. Okay, and now the question is, we want to know all the values of f of x, the polynomial original function, that are less than 0. That's the original question. We want to solve all the values. Okay, and in this case, it's an interval solution, and I want you to pay attention to this interval now that I'm going to draw for you. So look at this. This is below the less than 0 means below the x-axis, so this is the area. Okay, so all these x values right here. Then the next one is below, this is the area, right? So that's the area below, so that means this is the area. Okay, so we have minus 1 and 5, and the way you write it, you have to write it as an interval. The first part is x is between negative 1 and 1, and also x is between 1 and 5, and notice that I did not include these x-intercepts because they're strictly less than. Therefore, this is your final solution to this polynomial inequality.